So I'd like to start by acknowledging my co-authors, Mark, Siddhant, and Misha from Los Alamos, and Pascal from Michigan, who's here. So essentially, I work on problems that are mostly motivated by infrastructure networks. So by infrastructure networks, I mean these huge scale networks that operate at the scale of a nation or multiple nations, things like the power grid, or the natural gas pipeline grid, or the transportation network. And essentially, these provide critical services like electricity and natural gas that are really the lifelines of a modern economy. So when you think about operating these networks in an efficient and sustainable manner, there are a lot of computational challenges that arise. And I'm going to talk about a few of these in the next few slides, but Pascal is going to go into a lot more detail tomorrow. So essentially, one of the challenges that would naturally arise is the problem of optimal resource utilization. So if you think about a power grid that's connected to various types of resources, you may have like a coal plant somewhere in the network. You may have a solar array somewhere else in the network. And nowadays, a lot of people are talking about what is known as the smart grid, where consumers of electricity also participate in regulation of the grid. So if you have an electric vehicle, you might be able to offer a service to the grid that you can charge and discharge depending on the needs of the grid. If you have an HVAC system, say in this building, again, you may be able to offer a service to regulate your consumption depending on the load in the grid. So you have all of these different types of resources. They're all connected via this very complicated, huge-scale network. And you have complex constraints on each of these resources. And on top of that, you have the network constraints that kind of couple everything that's connected to the grid. And in the face of all of these difficult constraints, you want to minimize the cost of operating the grid while maintaining the network limits, any kind of constraints on the different resources, and you may even have constraints on maybe emissions, total emissions that you want to produce from the grid. Another type of problem you might be interested in solving is arises from the stochasticity in all of these networks. Again, taking the example of the power grid, if you have a wind turbine connected at some point in the network and say a solar panel connected somewhere else, and you have some probabilistic information about how much power any of these sources are going to produce. So you have some prediction for how much wind is going to be there, or how much solar power is going to be there. And essentially, given these distributions of the production at different points in the network, you want to control the probability that something bad in the network happens. So something bad, an example of something bad happening may be that the voltage somewhere in the network goes too high, which would mean that some devices would trip out, or some transformers may blow up or something. And you essentially want to control the probability that something bad like this happens, right? So this is a different type of reasoning problem that you might be interested in solving on an infrastructure network. And there's other examples from things like market design as well. And essentially, the only thing I'm going to take away from all of this in this talk is that all of these problems require us to solve graph-structured optimization or inference problems, right? And the graph structure basically comes about because most of the constraints that model the network essentially only couple neighboring elements in the network, right? So typically, the structure of these optimization or inference problems requires us to reason about systems of constraints and optimization problems that typically only couple local elements in the network. But overall, because of the interaction, you have a global coupling of all of the devices. So there's this very nice framework which has been popular in machine learning of what are known as graphical models that are essentially a tool to reason about graph-structured optimization or inference problems. So graphical models can encode succinct representations of either a constraint satisfaction problem or a probability distribution or an optimization problem. And they appear in various flavors. The flavor that I'm going to use in this talk is what are known as factor graphs. So factor graphs are essentially bipartite graphs which split the problem into two parts. On one side, you have the variables, and on one side, you have factors. Factors can either represent constraints in your problem, or they can represent terms in a factored optimization problem, or they can represent terms in a probability distribution. So There's lots of things that can be encoded in this form. If you take the example of constraint satisfaction, essentially what the factor represents is a constraint, and the variables that it is linked to are the variables that participate in that constraint. So here you have one constraint that depends on the variables x and y, and another constraint that depends on the variables y and z, right? And what this structure helps us to do is to encode what is known as conditional independence. So conditional independence basically means that if I fix the value of the variable y in this problem, essentially the problem decouples over x and z. So I can reason about x and z independently if I fix the value of y, because the only way those two variables interact is through the value of this variable y, right? Can everyone see that? So essentially, if I fix the variable of value of the variable y, I can decompose the problem into two independent subproblems and essentially solve them independently and combine the results. So this is really the computational advantage that I get out of this structured representation. And so let's see how I can exploit this algorithmically. So let's look at this simple factor graph where you have these factors phi1, 2, phi2, 3, so on, phi n minus 1 n. Each phi depends on successive pairs of x's, so phi1, 2 depends on x1 and x2, phi2, 3 depends on x2 and x3, so on, phi n minus 1 depends on xn minus 1 and xn. And let's say that it encodes this particular optimization problem where I want to minimize over all possible assignments to the variables x1 through xn, the sum of each of these terms, right? So this is a particular structured optimization problem. And let's see if we can exploit the factor graph representation to solve this problem efficiently, right? So the essential idea is to use this conditional independence structure and essentially start doing a recursion at one end of this chain. So I'm going to fix the value of xn minus 1, and I'm going to solve the problem of minimizing the last term, which depends on both xn minus 1 and xn with respect to xn. Okay? So this is the only term in this optimization problem that depends on this variable xn. So I'm going to solve the optimization over xn for each fixed value of xn minus 1. In this case, because they're all binary variables, there's just two values. And so I denote this minimized function in terms of xn minus 1 as this hn minus 1. So essentially what I've done by doing this minimization is to replace this part of the factor graph by something that only depends on xn minus 1, right? Does that make sense to everyone? Okay. So now I started with a factor graph over n variables. I reduced it to a factor graph over n minus 1 variables. And now I can continue to do this recursively. So I have a factor graph over n minus 1 variables, and now I can do a minimization over xn minus 1 for each value of xn minus 2 and get a factor that depends on xn minus 2 and keep doing this recursively until at the end I'm left with a single factor that depends just on x1, right? So if you're familiar with dynamic programming, this is exactly dynamic programming, and you might have seen it in various flavors. It shows up in all kinds of contexts. So the advantage of exploiting this recursive structure was that I was able to find the optimal value in time order n versus order 2 to the n, which would be the time taken if I just did the brute force approach of enumerating all possible assignments. And the same type of algorithm works not just for binary variables, but for arbitrary discrete variables that take values in some finite set 1 through k, and not just for these special types of chain graphs, but arbitrary tree structured factor graphs. So as long as you have a factor graph that doesn't have cycles or loops, you can apply this type of algorithm, and your overall complexity is going to be order k square times n, where k is the number of values that each xi takes. Okay? Okay, and it works not just for trees, but what are known as low tree width graphs as well. If you don't know what that means, don't worry about it. Okay, so I talked about infrastructure networks and the fact that they require us to reason about these graph structure optimization and inference problems. And I talked about graphical models, which are a very nice way to exploit graphical structure to solve these computational problems efficiently. So let's think about whether we can apply the graphical model framework to these infrastructure network problems. So the first thing I'm going to look at is a somewhat abstract model of infrastructure networks, but actually the model really captures the essential complexities of most infrastructure network problems. So I'm going to look at a model where I have an infrastructure network represented as an undirected graph. At each node in the network, I have a production of some quantity Qi. So this is the quantity that's being injected at this node. You can think of it as an injection of electric power, an injection of natural gas, or an injection of some traffic flow into a traffic network. And at each node in the network, I have some physical variable that lives there. The physical variable corresponds to something like voltage or pressure. And on the edges of the network, I have flows. Okay? And because these are physical flow networks, I have the constraint that the flow is actually a function of this variable x at the two ends of the line that the flow is on. Okay? So if you remember from your electric circuits course, the flow of current on a wire is driven by the difference in voltages at the two ends of the wire. The flow of pressure, the flow of water or gas is driven by the difference of pressure at the two ends of a pipeline, right? So this is a fairly flexible model that captures essentially most physical flow networks that you could think of. So I have these constraints that the flows are functions of these x variables. And then I'm going to have conservation of flow as well, right? So whatever is injected at this node I is equal to the sum total of the flows that are going out of that node, right? So I have these three edges, ij, ik, and il. So the qi is going to be the sum total of fij, fik, and fil. Does that make sense? Okay. And note that I don't require in this model that fij is just the negation of fji. Because I can have losses in transmission as well. So this model is able to account for losses as well. Okay. So how do I translate this into a factor graph? The trick to doing that is to define these collections of variables. So I'm going to define this capital X as the collection of Qi, Xi, and X of all the neighbors of I. Okay. So in this example, I had three neighbors, J, K, L. So I'm going to put xi, xj, xk, xl, and qi all together into this one variable, capital Xi. And then all of these constraints that I defined here are going to be internal constraints on the capital Xi, right? So the conservation of flow and all of these constraints that say that the flows are functions of the x's, all of these constraints just now become internal constraints on the Xi. But I have to be careful because essentially when I define these collections of variables, I create duplicates. So capital Xi and capital Xj are going to share the little xi and little xj. And so I need a constraint that says that these two copies that I create are actually consistent between themselves, right? So because I did some duplication, I need to ensure that the duplicates are consistent among each other. And this gives me this pairwise constraint that links capital Xi and capital Xj. So if I take these two constraints and put them into a factor graph formulation, essentially I have these, the little x's on the nodes get replaced by these capital X's. So these are going to be my variable nodes. And the factor nodes are these singleton factors that only depend on particular variables that encode all the physical constraints of the network. And I have these pairwise constraints that encode consistency between duplicates that I created when I formulated this problem, right? Okay, and you can see that the structure of this graph exactly mimics the original graph that represents the physical network, right? So essentially, I've told you a way of converting a physical network plus all of the constraints that are involved in it into a factor graph that exactly mimics the structure of the original physical network. Okay, so how do we encode problems that we're interested in into this model? The optimal resource utilization type problems could be encoded as follows. So you take these factors phi I and define them to be equal to some cost of production provided that the local constraints are satisfied and infinity otherwise. So just a simple way of pushing the constraints into the objective. And the same thing for the phi ij's. If the pairwise consistency constraint is satisfied, I incur a penalty of 0. Otherwise, I incur an infinite penalty. Okay? And then I have the overall problem as just minimizing the sum of all of these terms. And essentially, this is going to enforce that I'm trying to minimize the total cost of production subject to respecting all of the physical constraints in the network. Okay? Does that make sense to everyone? Okay. Similarly, I can encode these probabilistic reasoning problems as well. So if you remember this example, I have this stochastic production of the quantity at different points in the network. So I create these factors that just reflect the probability distributions of those quantities Qi, but only if the constraint is satisfied. So I essentially assign 0 probability to any configuration of the variables that does not respect the physical constraints in the network. And then if I want to bound the probability of some bad event that some variable xi goes outside a safe domain, essentially I just need to compute this integral of this product of terms. Okay? So this is the probability that this variable xi goes outside some safe region, given that the Qi's obey these probability laws. Right? Okay. So I told you how to encode these infrastructure network problems as graphical models. The other nice thing is that tree structure networks actually arise fairly often in infrastructure networks. So in electric grids, what are known as the power distribution networks, which connect substations to individual houses or consumers, these are typically tree structured networks. In gas as well, oftentimes, at least in the US, the gas pipeline network is largely tree structured. So tree structured networks arise often, and we have this graphical model framework that allows us to solve inference and optimization problems on tree networks efficiently, but there are still some challenges to be addressed before we can apply the graphical model methodology. So the first thing is that typically these graphical models have a mix of both discrete and continuous variables. So if you remember this parameter k, which is the number of possible values of my variables, this parameter is infinity. So if I apply, I can't directly apply the graphical model inference algorithms to this problem. The other issue is that typically the physical flow constraints, so the ones that I described here, these f functions are typically nonlinear, and so I have non-convex constraints that arise in this problem. And because these are critical infrastructure networks, maintaining these physical constraints all the time is really important. So I can't afford to ignore constraints in my problem. And typically, this is not something that the graphical model literature has looked into very carefully. So the way we're going to deal with these issues is fairly straightforward. So we're going to take the continuous variables and do some kind of discretization on them, and I'm going to describe exactly what type of discretization we do. In order to deal with the non-convex constraints, we're going to use some CP techniques, which involve both interval relaxation of these constraints and constraint programming. I'm sorry, this epsilon should be somewhere else. In order to maintain feasibility, I will show you that as we refine the discretization of these variables, we can essentially get all the way down to an epsilon tolerance on all of the constraints. So for any fixed parameter epsilon, we will be able to guarantee that all our constraints are satisfied up to that tolerance epsilon. Okay? So this is what we're going to shoot for. So let me start by describing the discretization process. So let's say that your variable xi is allowed to take values anywhere inside this box. Okay? So xi is a continuous variable that can take values anywhere in this box. What we're going to do is to partition this box into a number of cells. And essentially, we're going to define this discretized xi, which basically does not give a precise value to xi, but rather just says that it's in the first cell, or it's in the second cell, or it's in the third cell. Okay? So rather than specifying a precise value for the xi, I'm just going to tell you that it lies within this cell. Or essentially, I'm going to give an interval value to the xi. Okay? And then we need to do something about the constraints. So previously, I had a constraint that requires a precise value of xi. Now I'm going to do a relaxation of that constraint that says that rather than specifying a precise value of xi, I'm going to say that there is some xi inside one of these cells that satisfies the constraints exactly. Okay? And similarly, for the pairwise constraint, I'm going to say that there is some pair of values that satisfies the constraint exactly. Right? So does that make sense to everyone? So basically, I'm only allowing my xi's to specify which of these cells I am in. I'm not specifying a precise value. So I need to essentially change the constraints to say that there is some value in that cell that satisfies the constraint. Okay? So I'm not going to have a precise value that exactly satisfies the constraint. I'm going to say that there's the cell, and there's some point in that cell that satisfies the constraint. Okay, so this is all well and good. It allows us to convert a continuous problem into a discrete problem and at least think about applying the graphical model methodology. But unfortunately, even to determine the satisfiability of the statement, I need to solve a non-convex feasibility problem, right? So I need to determine whether or not there is a value of xi that satisfies this non-convex constraint fi of xi equals 0. So in order to deal with that non-convexity, what we're going to do is again apply a standard CP trick where we're going to take a convex envelope of the non-convex constraint. So essentially, if you have a non-convex constraint that says that you have to lie exactly on this blue curve, right? And I know that the domain on the x-axis is between 0.3 and 0.7, what I can do is to take the tangent to the curve at the two corners and join the chord as well. And then say that rather than lying exactly on this blue curve, I can lie anywhere within this triangular region, right? So I started with a non-convex constraint that says that I have to lie exactly on this blue curve. I relaxed it to a convex constraint that says that I can lie anywhere within this triangular region, right? And you can see that as the bounds on these variables gets tighter, the difference between the triangular region and the curve gets smaller and smaller. And this is what allows me to make my epsilon guarantee, that essentially, as I refine my discretization on the variables, even though I started with a non-convex constraint, I can do a convex relaxation of it that gets as tight as I can. Okay? And this is really the slide where all of the CP stuff comes in. So we're using this very nice technique from Carlton Coffrin, who had a paper at CP last year on doing bound tightening so that we can do efficient discretizations of these variables. And we also do some adaptive discretization tricks where as we do the dynamic program, we refine the domains of the variables on the fly. So there's a lot of tricks into implementing this practically, but I don't have time to get into that right now. Okay, so if you put all of these pieces together, at the end what you get is an algorithm that can find an epsilon feasible super optimal solution. And I say super optimal because we're allowing ourselves to cheat a little bit, right? So we're relaxing the constraints a little bit so we can find something that's better than the global optimum, but it's going to violate the constraints by some parameter epsilon. And we can do this in time order linear in the number of, in the size of the network, and polynomial in 1 over epsilon, where epsilon is the tolerance that we're trying to shoot for, okay? And the exponent essentially depends on the dimension of this variable xi that I looked at, okay? So for power grids, I can show that I can choose this d to be 3, and you can actually make similar guarantees for these probabilistic reasoning problems as well, not just for optimization problems. So if I apply this to the power grid problem, which is known as AC optimal power flow, this is a non-convex mixed integer problem, strongly NP hard in general and weakly NP hard in trees. I essentially can find an epsilon feasible superoptimal solution in time order n times 1 over epsilon to the 7. Okay. So this dependence on epsilon could be problematic in the worst case, and that's really what we're alleviating using these CP techniques where we do this adaptive bounding and discretization, which allows us in practice to get much better than the 1 over epsilon to the 7. Okay, so just to give you some context for what people have done in trying to solve this AC optimal power flow, there's been a lot of interest in using convex relaxations to solve these problems efficiently, and there have been very nice results obtained on showing when these convex relaxations are able to solve these problems tight, right? So they're guaranteed to find a feasible and optimal solution to these problems. Unfortunately, they require certain special conditions on the network, which are not always guaranteed. And also they can't handle integer variables, which is very important in these infrastructure problems where you need to like turn on and off devices. So there's very natural ways where integer variables arise in the problems. So there's limitations to all of these. And further, because they're based on a centralized convex optimization formulation, distributed implementation of these algorithms is not completely straightforward, and they can't handle these probabilistic inference type problems as well. Our approach is able to fix all of these problems, but at the expense of tolerating some approximation and suboptimality. There's also a lot of work in constraint programming. Rena has worked on a lot of these problems. Another domain where very similar ideas show up are in what are known as graphical games, which are games with certain graph theoretic structure, and you're interested in optimizing or computing Nash equilibria in these games. And recently, there's a work by Dan Beanstalk that does an abstract LP-based formulation, which is, you can kind of show it's roughly equivalent to the approach that we take, but they don't exploit constraint programming, and they don't have this graphical model interpretation, so they're not able to do probabilistic analysis type problems. So we implemented this and compared it to a bunch of solvers. I'm not going to go into the details because I'm short on time, but essentially what we find is that for simple problems, there are other solvers that are able to solve globally these problems in a smaller amount of time than our solvers. But we can create these difficult instances where there's very difficult, where there's non-conventional patterns of power flow in the network, for which these other solvers are not able to find solutions at all, whereas given enough time, our algorithm is able to find a feasible and optimal solution. So I'm going to skip over this future work slide and leave some time for questions.
Thank you very much.